Hey, good morning, good afternoon. Hope everybody's having a great M&M meeting. My name is Ray Tweston, Product Manager for Analytical at Gatan. I want to welcome you all to our Spotlight video, or our Spotlight presentation. There's been a slight change in program. About 18 hours ago, our high tension tank blew up on one of our microscopes. So we had to jump over and set up a demo on our other microscope. So unfortunately, we won't be able to demonstrate the EELS and EDS acquisition, but we will be demonstrating high-speed chemical mapping using the K3 direct detection continuum. And that's mounted on our Joel F200 cold FEG in Pleasanton, California. Our presenter is Paolo Longo, and if you don't know Paolo, he's a Director of Applications for Gatan, has been with the company for oodles of years, and has been all around the world showing EELS to people and learning new techniques and training people how to do EELS. So without any further ado, one other thing is that I will be monitoring the chat window. And try to answer the chat questions as they come in. We might have a little bit of time at the very end, but we will try to get to all the chat questions either in real time or after the presentation. Okay, so without any further ado, let me hand everything off to Paolo. Go ahead, Paolo.
Hello to everyone, wherever you are. Like Ray mentioned, I hope you guys are enjoying the meeting, the first virtual MMM. So basically, we were supposed to do some EELS and EDS, but like Ray mentioned, we have some problem with the microscope. So instead, we're going to be demonstrating, and we're gonna run like a live demo of counting EELS using the K3 continuum here in Pleasanton. So I'm going to share the screen. So here is the digital micrograph screen. So basically, so I don't know exactly who's here in the audience, but I'm going to walk you through a little bit of like GMS frame, which is the software we released a few years ago. And then we'll jump into, the data acquisition, and I'm going to walk you through what you could do with, with the K3 and counting EELS in particular. So we have the way the software is set up here. We have two different sessions. One is the instrumentation session, where everything related to the instrumentation is displayed. So you see the microscope right now. You see that we are blanking the beam. So we can actually control pretty much everything on the mic. Not everything, but we can control quite a lot using digital micrograph on the microscope. We can close the valve, but you see the camera length here we're using. We have the microscope already like in scan mode. You can blank the beam. So right now the beam is blanked. The screen is up. We're gonna be using the detector that is sitting right above the GIF. And we are in EELS mode already, and the K3 is inserted. So basically, this system here is got like two detectors at the end. The K3 is sitting before the other detector. The K3 is a direct detection detector, whereas the other detector, I can retract the K3. The other detector is a scintillator-based detector. So you can use, depending on the type of experiment that you're running, you can use one detector or the other detector. So the K3 can be operated down to 80 kV. So if you want to work below 80 kV, you can use the other detector. So when you click on the detector, you basically can load the alignment relative to the K3 or the alignment relative to the other detector. So you can change dispersion and everything there. You have two aperture here. In this case, is a 1 millimeter and 5 millimeters there. Okay. So we're going to be focusing on direct detection. So let's put this detector back. And now on the right side, now we have the software set up for EELS stem analysis. So the first session is basically what you need to acquire an image. Then we have the SI spectrum imaging setup acquisition that in general you need only to set up your STEMSI experiment, EELS, single EELS, two EELS. You already see like a difference, something that is kind of like a new with the K3, which is dual EELS. We didn't have dual EELS with the K3. Okay, so let's scan the beam, open up the beam blanker. So this is our sample. This sample is a FinFET device. This is from the latest technology of transistor, and we're looking at the contact region. So this is actually the contact region, very important, probably one of the most important regions. Is rich of chemistry, and we're going to try to analyze the chemistry during this presentation, during this demo. Okay, there's quite a lot of elements here, probably like 8 or 10 elements here. First thing you want to do, you want to try to focus the image. So we can use like a new feature that we developed with GMS3 as a focus loop. You can increase the dwell time inside, increase the number of pixels with the arrow key. And we can focus to get like a sharper image, something like that. Okay, so now let's focus on the EELS part. So we can stop the beam. So now we start the one. We'll try a couple of. I'm going to show you like a couple of acquisitions. So one is single range. So we go to 0. Let's look at the zero loss peak here. So you see very nice and sharp zero loss peak here. You can align, put it to 0. So we're using a dispersion of 0.9 that multiplied by 3,500 pixels gives you about 3,000 EV energy range. So this is the energy range that we have available with the Continuum. So if you look at the previous generation, we couldn't get that. So you see that it is already like pretty sharp, but you know, you can make it even sharper. Just play a little bit with the focusing here. There's also automated focusing available. So if you look at the full width of maximum, we have 1 pixel wide, which is what we expected. With dispersion, we have 0.9. So we have 0.9 EV energy resolution over a 3,000 EV energy range, which is actually pretty amazing. And this is actually a major step forward compared to the previous technology. So now we go to 500 here. So we are changing the energy. We open up the shutter now. So this is all the spectrum that we are collecting. So you see a very nice tungsten there. So, and we're going all the way to 3,400 EV. So you're going from about like 200, 250 to 3,200 EV. Okay. So very wide energy range. So let's scan the beam. Okay, so first thing, let's look at the preview image. So we're getting a little bit higher quality image. You see all these elements, all these atoms like popping up. Let's look at a very large area. So here we are, this detector, the K3, for those of you who are not super familiar, it basically doesn't have any scintillator. So we are exposing the sensor straight to the electrons. So that actually improves a lot the point spread function, actually reduces the point spread function, but it also, because we're counting each single electron, so we are nearly eliminating all the instrumental sources of noise. Let's look at very a wide region. So you can control, you know, the exposure time here. So let's use it with about like 5 millisecond exposure time. So, and you can control the number of pixels here, or if you're interested in a 1 nanometer resolution, you can say 1 nanometer resolution. And now live mapping. So this is a feature that we added in with the GIF Continuum. So you can click on live map, and while you are acquiring the spectrum image, the software will generate some maps. So you can go on the periodic table, or if you're looking at the same material system all the time, or you know, like a defined number of material system, you could go in there and select your recipe. So these are all the elements that we have in this region of the specimen. These are all selected. And now at this point, you can just go and say capture. So we're using 5 milliseconds. So the software now is gonna scan the beam across this region. You see the EELS spectrum here, and pixel by pixel is generating elemental maps. So like I said, this is something that we didn't have before, and now is available. Even at high speed is already able to separate tantalum. You see here the tantalum is already able to separate tantalum from silicon and from tungsten. You start to see some tungsten there. And you see like quite a lot of titanium. And you see like oxygen and nitrogen. This is done at pretty high speed. You see the copper also looks pretty nice here. So, very soon it'll be done, and then we can generate some color maps. And then the next experiment I want to show you is actually to run this system on even higher speed. So after we finish the acquisition, so the acquisition is done. And now the software is going to compute, is going to recalculate all the elemental maps, because what you see here is something that was calculated like on the fly. Okay. So you can even use color mix and put all these elements together. Germanium, oxygen, and nitrogen. And you get like a very nice elemental map. You see like pretty much all the elements. What about going faster? So this system, the K3 actually can run. So the old map took like a minute. What about we run this at top speed? So the top speed of the K3 is actually 3,000 spectra per second. So I could go down to 3,000 spectra per second. It took in total like a minute. So I could go there and say like a minute here. So some frames. So essentially the approach that I'm using here is something that it was kind of like developed for these fast EDS detectors. So essentially I'm going to scan the entire frame, and then I'm going to sum, I'm going to go back to the same frame again, and then scan another one, and I'm going to sum spectra continuously. So the software is telling you that if I do 10 frames, it will take 41 seconds. So I want to go to about like a minute, okay? And you can also apply drift correction during the acquisition. So let's click on drift, and we want to do each single frame. So you want to put this in a good region here, something like that, that shows you a little bit of contrast. And now we are ready to start. So it's going to do 16 times. It will go through the same area, and it will sum spectra. But each spectra will be acquired with 0.3 millisecond exposure time. So we are essentially running the system now at 3,000 spectra per second. So this is going to be incredibly fast. So the software started very fast. It's already generated elemental map. So I mean, the system now is running actually faster than the software is capable to generate the map. So the software will skip certain pixel to actually keep up with the software and give you like a map. But it's already able to separate tungsten from from the silicon. And I can see there's tantalum here. And each single pass, the quality of the maps will get better and better. In the end, the software will recalculate all the maps. So now we are running at 3,000 spectra per second. And, I think it's displayed somewhere down here. So you can see the speed. There's a 100% duty cycle. So essentially the system is 100% efficient. So there's no any loss in time. So you're taking advantage of all the electrons available for your experiment. Something that we could do with this system that we can do with a scintillator-based detector is, in the case of a scintillator-based detector, you have to, you basically suffer of, instrumental sources of noise, in particular readout noise, gain noise, and photo conversion noise. But if you're able to count each single electron like we're doing right now with the K3, you're able to get rid of all the instrumental sources of noise, and now you're purely limited by the shot noise. So essentially you can go as fast as you can, and then you sum frames, and then eventually you get to the same point. If I use the same detector, you wouldn't be able to collect anything. You would just collect pure noise. So So we've done 16 frames, and it's basically like a worth of a minute of acquisition. We're spending more time in drift correction than actually taking data. But I just wanted to show you in case, you know, you just put the sample in or your sample is really bin sensitive, you could definitely use this approach. Because again, you're only limited by the shot noise. So now the software finished the acquisition. So we did 3,000 spectra per second, and now it's gonna calculate all the maps. So it's because, you know, going like very, very fast that we skip certain frames. So now the software is doing like a better calculation of the maps, and we're back to the same point we were before. So let's do again another color mix. And it's about the same as before. There's no any mathematical processing involved. We're able to separate the tantalum from the tungsten. What about looking at quality of the spectrum? So the quality actually looks pretty good. I can even see the tungsten M23. And these spectra were actually acquired with 0.3 millisecond exposure time. So we're going at 3,000 spectra per second. Another thing that actually, that in my opinion is very important when you run this, you collect the spectrum imaging, is actually what happened at the end of the acquisition. So with GMS3, you can tell after the acquisition, or you want to blank the beam, or you want to close the valves. Imagine you want to go home, you don't have to fill up the liquid nitrogen or run the ACD. You can just tell the software to close the valves. So in this particular case, I want to tell the software to blank the beam. Okay, so let's do another acquisition. Open up the blank. So you see already like the good quality of the spectrum. But what about we do one single frames at very high speed? Just one pass. I just want to show you how good this map is. 4 seconds map. Again, live mapping again. So the software now is going to blank the beam. So let's see if the software, let's see if we could get in 4 seconds, we could generate a good map. So the software now is going to calculate the maps again, because, you know, we were going way too fast. And now it's going to do recompute the maps, you know, pixel by pixel. So we're actually spending more time on processing the data than acquiring the data. This took only 4 seconds to collect this data. And, you know, we're still, it's pretty amazing because you're still able to separate the tantalum from all the other, from the tungsten and the silicon. This was done with 0.3 millisecond exposure time. So again, we could do the same thing, color mix, because colors are good. And now our map is actually, you know, we're getting the same information as the other one. Of course, you know, we have 16 times more electrons in this map because we we acquired 16 frames. But that shows you again the quality of these, the quality of actually counting EELS and the K3 in this particular case. Something else that we developed that we introduced with the K3, we didn't have with the K2, is a dual EELS. So I'm going to show you dual EELS. So let me stop the beam there. And for those of you who are familiar with the quantum, I'm sure you're familiar with dual EELS. You know exactly how to set up a dual EELS. So we go here, dual EELS. Now we have 2 different columns. One that will be used to control, you know, the low loss, and the other one used to control the high loss. We also have zero loss peak lock because sometimes with the acquisition of zero loss peak can jitter. And the same stability is actually reflected onto, you know, the core loss. But if you're able to acquire low loss or core loss, you can correct for that. We could do this actually live with the zero loss peak lock. Okay, so we are collecting low loss and core loss with the K3. So again, it's only 1 pixel here, so the energy resolution is still pretty good. Okay, so now I want to focus a little bit on these regions here, because I know there's quite a lot of chemistry happening there. So we have to bump a little bit the exposure time here to get a little bit better data set. And now we're going to go across across this region here, and we'll do in dual EELS mode. So we're collecting low loss, core loss together. But now we are interested in quality. So we want to look at we're going to look at the fine structure of titanium and nitrogen, see if there are any changes in there. Still a relatively short exposure time. We could use also the other approach we used before to some frames, but this is basically the advantages of using these detectors. So it gives you a lot more flexibility when you collect the data, which is actually important because you don't look at the same type of material all the time, but you might come across materials that are quite beam sensitive. So you want to have the ability to change your setup or change the experimental conditions without affecting the quality of your data. So this is almost done. So there's quite a lot of layers of titanium with fine structure of titanium changing. And again, we're using a very low, we are actually using the lowest dispersion to give like the largest energy range. Okay, so the software like blank the beam. All right, let's look at the quality of the data. So right click here. And you can mirror this. You can also mirror with you can also mirror this with a simultaneous image. So you have low loss here. This was acquired with a very short exposure time, but you also have core loss here. Like I mentioned before, we're interested in titanium, so you see like very good quality of the titanium here. We can make it a little bit smaller. And then you see this is a typical structure of titanium nitride. Let's look at the oxygen as well. But here you have quite a lot of oxygen. And this is actually a typical structure of something bonded to the oxygen. It's probably titanium oxide in this region. But again, you have enough quality to look at all the fine structure of this element. Again, you see this is a titanium oxide. There's no nitrogen anymore. And then you get the nitrogen there, and the shape is slightly changing. And if you want to look, this is more detailed, we could probably change the dispersion using a little bit higher dispersion to get more pixel here. But this is possible even with this energy range. At the same time, you're collecting everything all the way to, you see the tungsten here. So basically, there's not really any compromise going from the chemical analysis and composition analysis. You get everything in the same data set. Okay. So we could probably try to change the dispersion to see this is a little bit more detail. So 0.45 will give you about 1500 dB energy range. Open the blank. Okay, we probably have to focus the spectrum a little bit. Nearly 1 pixel again. I think the microscope doesn't have the energy resolution. So we're actually doing, you know, nearly like the best of what is available, is achievable with this microscope. Okay, so we kind of like focus the spectrum. So we're interested again on nitrogen and titanium. So maybe you want to move a little bit down, 400. Okay, so now we have nitrogen here, titanium, and everything together. So we can try the same, exactly the same acquisition. Okay, and now we're going to capture here.
So Paolo, just a heads up, we're coming up to 5 minutes left in the session.
Yeah, so this acquisition should be done in 60 seconds, 50 seconds, and then I can just take questions.
We did have one question. What's the beam current we're running at here?
It's about 200, 250 picoampere current.
Okay, thanks.
I will really measure the beam current. This is a gray specimen. It's very, very thin. So it's also not generating much in elastic scattering. So it would be nice to have a little bit thicker specimen to get a little bit more signal. So this should give you like a very good quality of you know, the titanium edge. So we can look at more details, the chemistry.
Are you allowed to say where you got the specimen?
I got the specimen from Evans Analytical Lab, Precision TM, Hongjiang. I made this sample with the fib, but I managed to make such a thin specimen with the fib, but it's super thin.
Yeah, they do a great job. Just want to say thanks for the specimen.
So let's look at this one here again, just a little bit more detail. So this is going to look even better because, you know, we have a little bit higher dispersion. You can see there. So you have a mix of, you definitely have titanium oxide in there. But you also have other phases of titanium. You also have titanium nitride. You have a mixture of titanium oxide, titanium nitride in there. And then you're getting deep in the tungsten. Yeah, I mean, this really detector can really make the difference, especially when you want to do any type of chemical work and composition analysis. It really gives you that edge, and experiments that were like impossible before are now becoming possible. And you can think about looking at polymers, or even looking at 2D materials at high energy now is possible because you can work with a very low dose. And again, the possibility having a very low noise and high speed, it opens up a lot of possibilities for new strategies of data acquisition. So this really makes the difference.
Great. Yeah, that was a wonderful demonstration, Paolo. One question was about when you're doing the dual EELS about correcting for zero loss drift. There is a feature we call zero loss peak lock, and I guess Paolo just forgot to click that button, but it allows you to on the fly correct for any zero loss peak shift.
Yeah, there's so many new features with you know, like GMS 3.4 that we're running here. That you know, like there are so many new features that we didn't have this available before, and now it's like available with all the Continuum. But it's actually important to notice that, and the width collect this map in 4 seconds. So to me, this is pretty amazing because we were able to separate tantalum from tungsten, as well as like silicon. There's silicon pretty much everywhere, and all these elements overlap massively. This was done in only 4 seconds. So that it's possible because we're using direct detection, and we are not limited by instrumental noise, and we still have enough quality to get some chemical analysis. So this was done at 3000 EV energy range, dispersion 0.9. And you can do a little bit better work, but you still have 1500 EV energy range. You get very nice fine structure for titanium. You can split you know, the pre-peak of the nitrogen. You can tell this is a titanium nitride, but at the same time, you have titanium oxide in there. So you get all the type of information in your data set. Okay, I don't know if there are any other questions, but you can reach out to us should you have any other questions.
Yeah, we're on 45 seconds remaining, and I've been told that it just goes blank when you hit the end of the timer. So I'll continue to answer questions online, and of course you can reach out to us, Paolo.longo@amatech.com and ray.tweston@amatech.com if you have any other questions. All right, Paolo. Hey, thanks a lot. This is very informative, really impressive how fast you can go on the system. Any final words?
Yeah, I mean, I want to thank everyone, and obviously it's like a pleasure to be able to use this system. It really makes a difference for data acquisition.
All right,
so
thanks
I want to
everybody.
thank everyone. Bye.
Cheers, bye.